You built a sleek AI demo. It runs locally, it generates great text, and the investors love it. But the second you try to put it in front of real enterprise users, it cracks. In 2024, deploying an AI feature often meant hooking up an external API and calling it a day. By 2026, companies have realized these systems are too fragile to support a business, and they've stopped paying for prototypes. To see what hiring managers actually want, we can plot development effort against system reliability. The bottom left quadrant is where local chat demos and basic API wrappers live. They're fast to build, but they lack the stability required for a production environment. The 2026 career trajectory moves toward the top right. This is where you find production systems, architectures designed to be as reliable as they are complex. Most candidates are still walking into interviews with resumes focused on machine learning theory. They're being rejected because they can't answer the real questions: stateful architecture, scaling costs, and LLMOps. Passing an interview today requires proving you can constrain, orchestrate, and observe models that are inherently unpredictable. The engineering focus has shifted away from simple prompting toward building the rigorous software safety net that makes a raw model viable for an enterprise. Your first architectural hurdle is getting a model to answer questions using private, dynamic company data without hallucinating. Fine-tuning changes a model's style and base behavior, but Retrieval-Augmented Generation, or RAG, injects external context at runtime. It gives the model fresh data without changing the underlying weights. This is a production RAG architecture. Ingestion and processing layers clean raw documents, breaking them into optimized chunks with metadata. The retrieval layer uses hybrid search to pull relevant chunks. Finally, the generation layer funnels that context into the LLM, ensuring a grounded answer. RAG provides verifiable citations and data privacy, but it introduces significant infrastructure complexity and higher user-facing latency. Designing these systems is a meticulous exercise in data engineering. If your retrieval accuracy is low, the entire system's output will be flawed, no matter which model you use. Beyond just retrieving knowledge, modern AI systems are expected to interact with external tools and execute multi-step tasks. We handle this through tool calling. Instead of letting a model guess a user's order status, we program it to trigger a specific API call, fetch the real database record, and explain the result. When a system can plan its own steps, use those tools, and work toward a specific goal, it becomes an AI agent. Agents require stateful workflows. Frameworks like LangGraph allow the system to maintain a memory of previous authentications and intermediate steps throughout a long-running process. However, giving an autonomous agent access to real-world infrastructure creates massive security risks and operational vulnerabilities. Production-ready agents must have guardrails, strict input validation, limited permissions for each tool, and aggressive retry logic for when an API fails. For sensitive actions, like a database write or a payment, the most important engineering decision is often implementing a human-in-the-loop bottleneck. A senior AI engineer knows exactly when to enforce these boundaries and when to replace an unpredictable agent with a simpler, deterministic workflow. This leads to the most critical part of the 2026 interview, proving that your system actually works at scale. In production, a hallucination or a failed tool call isn't just a random occurrence. It's a measurable bug that needs to be tracked. Engineers are now building specific test datasets and rubrics to evaluate the accuracy of an LLM before any code is deployed to users. You have to measure at every level: input-output safety, retrieval accuracy for RAG, and whether the model is passing the correct parameters to its tools. This entire architecture must be wrapped in a layer of observability and evaluation. This means you are constantly monitoring data streams for latency, token usage, total cost, and the rate of failed retrievals. Building these observability pipelines takes time, which slows down your initial shipping speed. But the defining characteristic of production AI is architectural visibility. You cannot fix or trust a system if you can't measure its performance. Your interview preparation strategy depends on where you are starting from. We can use this matrix to identify where you need to pivot your skills for a 2026 AI role. Traditional software engineers need to move beyond strict Boolean logic. They should invest in probabilistic evaluation, retrieval quality, and prompt security. Data scientists should shift their focus from model architecture towards system design. stateful application infrastructure, and optimizing for latency. And if you've mostly built API wrappers, it's time to move toward enterprise security, strict agent boundaries, and comprehensive observability. Hiring managers use these categories to find the weaknesses in your system design during the interview process. In 2026, simply making an AI sound smart in a demo isn't the goal. The goal is proving that your application is observable, cost-effective, and secure enough for high-stakes enterprise use. Your value as an AI engineer is measured by your ability to build the containment system that keeps raw model intelligence within predictable, useful bounds. The interview and the job comes down to whether you can wrap a non-deterministic model in a stable, production-ready architecture.